Some prehistoric animals do not look like ancestors. They look like mistakes that somehow worked. A whale with legs strong enough to walk. A snake so massive that the river itself became suspicious. A flying reptile built at a scale that still feels too heavy for the sky. A bird that could not fly, yet turned the ground into a hunting field with a skull longer than a human forearm. These were not fantasy creatures. These were real animals, shaped by real ecosystems, under pressures that made the modern world's categories look almost too simple. That is the unsettling part. Not that these animals were strange. The unsettling part is that evolution had a reason for every strange decision. Deep time was not a clean staircase leading toward the animals humans recognize today. Deep time was messier, harsher, and far less interested in familiar shapes. Earth was a testing ground, and the results were not required to look normal. In certain eras, the safest body plan was not the obvious body plan. The winning answer could be a walking whale, a giant snake, a clawed herbivore, or a mammal relative with a crocodile-like face and a crown of bone. These animals feel impossible because modern life teaches neat categories. Whales belong in open oceans. Birds belong in the sky. Snakes should not approach the mass of large predators. Herbivores should not need long arms tipped with claws. But ancient ecosystems did not care about modern expectations. Ancient ecosystems rewarded whatever worked. And under the right conditions, almost anything could work. The first impossible animal begins where land stops being reliable, not in the deep ocean, not in the wide blue world of modern whales, but at the edge of warm Eocene coastlines, roughly 48 million years ago, where river channels, coastal lagoons, mudflats, and estuaries blurred the line between land and sea. In regions like what is now Pakistan, fresh water mixed with salt water. Channels shifted with floods and tides. Vegetation crowded the banks. The air was heavy. The shoreline was unstable. Visibility beneath the surface could collapse into a brown, silent murk. For prey animals, that kind of landscape offered very little certainty. For the right predator, that kind of landscape was an opening. That predator was Ambulocetus natans. The name is often translated as the walking whale, but that translation can mislead the imagination. The word whale makes people picture something enormous, smooth, and fully marine, a body drifting through open water with no real connection to land. Ambulocetus natans was not that. Ambulocetus natans was a heavy amphibious hunter, a predator that looked less like a modern whale and more like an unfinished mammal stepping back into the sea with the habits of a shoreline killer. The body of Ambulocetus natans still had working legs. Not symbolic legs, not useless leftovers. Functional legs. The forelimbs of Ambulocetus natans and the hind limbs of Ambulocetus natans were strong enough to support the weight of Ambulocetus natans on land. That single detail is enough to make the animal feel wrong to modern eyes. A whale is supposed to be committed to water. A whale is supposed to have no walking body left. But Ambulocetus natans belonged to a stage before that commitment was complete. On land, Ambulocetus natans probably did not move with speed or grace. The skeleton of Ambulocetus natans suggests an animal capable of crossing ground, but not an animal built for long pursuit. The walking motion of Ambulocetus natans was likely heavy, awkward, and limited compared with a true terrestrial predator. That limitation matters, because evolution was not building Ambulocetus natans into a runner. Evolution was building Ambulocetus natans into an ambush predator. A heavy body becomes a problem in an open chase. But in shallow water, mud, riverbanks, and narrow channels, a heavy body can become an advantage. Mass can hold the predator in place. Mass can drag prey down. Mass can turn a brief moment of contact into a fight that prey animals cannot control. The real territory of Ambulocetus natans was not dry land. The real territory of Ambulocetus natans was not open sea. The real territory was the border between both. That is where the body of Ambulocetus natans begins to make sense. In water, fossil evidence and skeletal reconstruction suggest a swimming style powered by strong movements of the torso, with the hind limbs of Ambulocetus natans helping drive the body forward. This was not a modern whale cutting through deep ocean with a powerful tail fluke. The image is closer to a giant otter, a crocodile-like mammal, or a dense amphibious hunter using the full body to move through shallow channels. And that is where whale evolution becomes much less gentle than the popular version. Modern whales are fully marine mammals. Modern whales breathe air, nurse young, regulate body temperature, and still live in the ocean with bodies that, from a distance, can look almost fish-like. But that transformation did not happen in one clean step. The path from land mammal to ocean giant passed through bodies that lived between worlds. Ambulocetus natans was one of those bodies, and that middle stage was not peaceful. That middle stage had teeth. The jaws of Ambulocetus natans and the teeth of Ambulocetus natans suggest a serious predator. The teeth of Ambulocetus natans were not built for filtering tiny organisms from seawater. The skull of Ambulocetus natans was not the skull of a harmless grazer. Ambulocetus natans was equipped to bite, hold, and tear in a murky estuary where fish, reptiles, birds, and mammals could all approach the waterline. That kind of jaw turned the edge of the water into a dangerous place. The threat was not a long chase. The threat was one wrong step. A prey animal approaching an Eocene channel might see only mud, roots, vegetation, and still water. The head of Ambulocetus natans could remain low. The eyes of Ambulocetus natans could stay near the surface. The heavy torso of Ambulocetus natans could disappear beneath brown water. Then the attack would come from the place the prey animal had already decided was safe. The bite of Ambulocetus natans did not need to look elegant. The bite of Ambulocetus natans needed to be final. Once the jaws of Ambulocetus natans closed around slippery prey, the environment began working for the predator. On land, struggling prey can brace, twist, kick, or run. In shallow water, that leverage starts to vanish. Hooves lose traction, limbs sink into mud. The body becomes harder to control. The predator does not have to win a race if the predator can simply stop escape. Ambulocetus natans also reveals something deeper than a strange body plan. Ambulocetus natans shows evolution changing the way a mammal sensed the world. Modern whales here underwater with highly specialized anatomy. In early whale relatives, that transformation was still underway. Ambulocetus natans appears to have lived at a stage when hearing and vibration sensitivity were being reshaped for an environment where sound behaves differently, where vision can fail in turbid water, and where detecting movement through water can matter as much as seeing clearly. That makes Ambulocetus natans more than a strange predator. Ambulocetus natans was part of the moment when evolution began changing the equipment of perception. The eyes of Ambulocetus natans, the ears of Ambulocetus natans, the skull of Ambulocetus natans, the limbs of Ambulocetus natans, and the spine of Ambulocetus natans. all point to a body in transition. But transition does not mean confusion. The body of Ambulocetus natans worked because the environment rewarded that mix. Land allowed Ambulocetus natans to move between pools, banks, and resting places. Water allowed Ambulocetus natans to hunt. The combination only looks awkward if the modern viewer expects one animal to belong cleanly to one world. But survival often belongs to the animal that controls the boundary. Ambulocetus natans did not need to rule dry land. Ambulocetus natans did not need to rule the open ocean. Ambulocetus natans only needed to rule the edge. And from that edge, the future of whales began moving farther from shore. Over time, the legs of whale ancestors changed. The body lengthened. The tail became more important. The nostrils shifted upward. The skull, spine, limbs, and hearing systems continued to transform. The heavy amphibious hunter eventually gave way to whales that would never walk again. But before whales became ocean giants, one of the most important bodies in that story may have waded in muddy water. With legs still strong enough to carry weight, and jaws still dangerous enough to make the shoreline unsafe. The second impossible animal appears after one of the most famous catastrophes in the history of life. The non-avian dinosaurs were gone. The great Mesozoic predators had vanished. For many people, that sounds like the end of monsters, but extinction does not erase violence from nature. Extinction creates room. In the Paleocene, after the asteroid impact shattered the old world, ecosystems began to rebuild. Forests expanded. Rivers moved through humid lowlands. New food chains formed in spaces where older giants had disappeared. In what is now Colombia, in the region known from the Cerrejón coal mine, one of the most extreme predators of the post-dinosaur world took shape. Titanoboa cerrejonensis, a snake so large that the first serious warning came not from a beautiful, complete skeleton, but from vertebrae. That matters because the body of a snake is organized around the spine. In snakes, the vertebral column is not only support. The vertebral column is length, shape, movement, strength, and identity. When the vertebrae of Titanoboa cerrejonensis were studied, the message was not subtle. This was not a large snake in the modern sense. This was a snake in a different category. Titanoboa cerrejonensis is commonly estimated at more than 12 meters in length, with some estimates pushing even farther depending on the model. The mass of Titanoboa cerrejonensis may have reached hundreds of kilograms, and some reconstructions place Titanoboa cerrejonensis near the weight range of a small car. The exact numbers can shift depending on the method, but the conclusion does not collapse. Titanoboa cerrejonensis was enormous, and enormous size rewrites behavior. A snake at that scale is not just an ordinary snake, enlarged in a simple way. The body of Titanoboa cerrejonensis would demand energy. The muscles of Titanoboa cerrejonensis would need warmth to function well. The mass of Titanoboa cerrejonensis would affect speed, movement, buoyancy, and hunting strategy. The animal forces one basic question: how could a snake that large exist at all? The first part of the answer is heat. Snakes are ectotherms, meaning the body temperature of a snake depends heavily on the surrounding environment. In a cooler world, a snake the size of Titanoboa cerrejonensis would be slow, inefficient, and dangerously vulnerable. But the Paleocene tropics of northern South America appear to have been hot, wet, and intensely productive. Fossil plants and geological evidence point toward a rainforest-like environment, an ancient tropical system often compared to an early Amazon, but on a planet warmer than the modern one. That makes Titanoboa cerrejonensis more than a predator. Titanoboa cerrejonensis becomes a climate signal. The existence of Titanoboa cerrejonensis suggests an environment warm enough to support a giant cold-blooded body. Titanoboa cerrejonensis is not just an animal preserved in rock. Titanoboa cerrejonensis is a thermometer made of bone. But heat alone does not explain survival. Strategy does. Titanoboa cerrejonensis did not need to race across open ground. A massive snake is not built for long pursuit. The most reasonable hunting method for an animal like Titanoboa cerrejonensis is one of the oldest predatory strategies on Earth: ambush. A Paleocene river moves slowly through tropical forest. The water is dark. The banks are soft. Vegetation hangs low over the channel. Large fish move below the surface. Crocodiliform reptiles patrol the waterways. Giant turtles use the same edges. This is not a peaceful boundary between water and land. This is contested ground. In that world, the body of Titanoboa cerrejonensis would have been almost unfair. Part of the body of Titanoboa cerrejonensis could stay submerged. The surface might show only a ripple, maybe nothing at all. A prey animal entering the wrong channel would not see the full predator. That is the first advantage of a giant ambush snake. The danger stays hidden until the distance is gone. The strike would be short. The strike would be violent. The jaws of Titanoboa cerrejonensis would secure the first contact, and then the body of Titanoboa cerrejonensis would become the real weapon. Modern constrictors do not kill the way old movies often suggest. They do not simply crush bones for spectacle. Constriction works mainly by disrupting circulation and shutting down vital function. With Titanoboa cerrejonensis, the scale of the body made that pressure overwhelming. The prey did not need to be bitten apart. The prey needed to be held. That is a colder form of predation. No roar, no chase across open plains, no raised claws. Just contact, pressure, and time. The ecosystem of Titanoboa cerrejonensis contained prey large enough to make such size useful. Large fish, ancient crocodile relatives, and enormous turtles lived in and around the same waterways. A smaller constrictor might struggle to control heavy armored prey. Titanoboa cerrejonensis could use water and mud to remove the prey's leverage. In water, the weight of Titanoboa cerrejonensis became less limiting. The body of Titanoboa cerrejonensis gained support. The prey lost footing. That is where the river became part of the weapon. For animals living near the cerrejon wetlands, the danger was not simply that Titanoboa cerrejonensis existed. The danger was that the environment allowed Titanoboa cerrejonensis to remain almost invisible until the attack had already begun. Titanoboa cerrejonensis proves that the world after the non-avian dinosaurs was not a softer sequel to the Mesozoic. The cast had changed, but the pressure had not vanished. The extinction of non-avian dinosaurs opened ecological space. Mammals had not yet fully occupied every large predatory niche. Reptiles still had room to become giants, especially in hot tropical systems. And in one of those systems, a snake became the kind of predator modern biology almost refuses to repeat. Titanoboa cerrejonensis did not need horns. Titanoboa cerrejonensis did not need legs. Titanoboa cerrejonensis did not need a skull full of serrated teeth. Titanoboa cerrejonensis turned the river into a trap. The third impossible animal comes from a time before dinosaurs, before mammals, before familiar forests, and before vertebrates fully took command of aquatic ecosystems. In the early Devonian, the world was still negotiating who would dominate. Life on land was beginning to change, but water remained the main stage. Rivers, deltas, lagoons, estuaries, and coastal systems held animals that do not fit comfortably inside modern expectations. Some fish carried armor. Some predators carried external skeletons. And some of the largest hunters were not vertebrates at all. One of those hunters was Jaekelopterus rhenanii. Jaekelopterus rhenanii was an eurypterid, part of the group often nicknamed sea scorpions. The nickname creates the right feeling, but the science is more precise. Jaekelopterus rhenanii was not a true scorpion. Jaekelopterus rhenanii was an aquatic arthropod, a distant relative of horseshoe crabs and arachnids, protected by an exoskeleton and equipped with front appendages built for seizing prey. The size is the first shock. Jaekelopterus rhenanii is one of the strongest candidates for the largest arthropod ever known. Estimates often place Jaekelopterus rhenanii around 2.3 to 2.6 meters long. Part of the evidence comes from a large fossil chelicera found in Germany, a front-grasping appendage that immediately pointed to an animal far beyond the scale of ordinary modern arthropods. At that size, an arthropod stops feeling like an insect. Mechanically, Jaekelopterus rhenanii becomes an armored predator. The exoskeleton of Jaekelopterus rhenanii acted as protection. The chelicerae of Jaekelopterus rhenanii acted as tools for grabbing, cutting, and controlling prey. In modern waters, most large aquatic predators are vertebrates: sharks, crocodiles, marine mammals, and large fish. But the Paleozoic world did not always distribute power that way. There were moments when giant arthropods occupied the role of apex hunters. That alone breaks the modern picture. Jaekelopterus rhenanii was probably not a deep, open ocean monster. Fossil evidence points toward freshwater or brackish environments in the Rhineland region of Germany. That actually makes Jaekelopterus rhenanii more uncomfortable to imagine, not less. Instead of a distant animal lost in dark sea depths, the more realistic setting may have been shallow water, channels, lagoons, deltas, and estuarine systems. Exactly the kinds of places where visibility and escape can fail. The main weapon of Jaekelopterus rhenanii was not a venomous stinger like that of a modern scorpion. The main weapon was the front chelicerae. In pterygoid eurypterids, the group that includes Jaekelopterus rhenanii, the chelicerae could become large and specialized. Studies of related eurypterid structures support the idea that some of these animals could attack resilient prey, possibly including armored fish. That matters because Devonian fish were not simply modern fish wearing older designs. Many Devonian fish were deeply strange, and some, including placoderms, carried bony plates around the head and body like shields. A predator attacking that kind of prey needed more than speed. A predator needed grip. The chelicerae of Jaekelopterus rhenanii gave Jaekelopterus rhenanii a way to control the first moment of contact. In shallow water, the attack may have been brief, mechanical, and brutal. A segmented armored body rises from beneath or behind. The chelicerae of Jaekelopterus rhenanii close. The prey loses the ability to choose direction. This is not mammalian violence. This is mechanical violence from a body made of living armor. Vision may also have mattered. Some eurypterid lineages show evidence of advanced visual systems. Jaekelopterus rhenanii did not need mammal-like intelligence to be dangerous. Efficient sensory input, a short burst of movement, and appendages capable of grabbing hard prey could be enough. In a channel where armored fish moved through shifting light, the animal that detected motion first had the advantage. But giant arthropods carry a hidden cost. They molt. Arthropods grow by replacing the exoskeleton. That means a large arthropod must periodically pass through a vulnerable stage. During molting, the protective armor is compromised. For a small arthropod, that is dangerous. For a giant predator like Jaekelopterus rhenanii, the problem becomes extreme. How does an animal with such a large exoskeleton survive the moments when that armor is not fully functional? The answer was probably behavioral and ecological. Jaekelopterus rhenanii may have used sheltered places, chosen safer moments, and reduced exposure during vulnerable stages. But there is also a colder possibility. In the right habitat, even the vulnerable phase of a dominant predator may be less dangerous than the normal life of almost everything else around the predator. That does not mean Jaekelopterus rhenanii was invincible. It means the ecosystem temporarily allowed an arthropod superpredator to exist. Over time, the balance changed. Vertebrates diversified. Aquatic food chains shifted. The age of giant eurypterids faded. The role of armored arthropod ruler became increasingly rare until that role disappeared from the world. That is why Jaekelopterus rhenanii feels impossible now. Not because biology could never build Jaekelopterus rhenanii, but because modern ecosystems no longer leave that position open. There was a time when a shallow Devonian channel could hide a predator longer than a human body. Covered in armor, armed with grasping chelicerae, and living in a world where fish had not yet fully taken control. No roar, no tyrannosaur jaws, just a segmented body breaking the water and a pair of front appendages built to end the struggle before the prey understood the rules. The fourth impossible animal is not unsettling because the animal crawled through mud or waded under dirty water. Quetzalcoatlus northropi is unsettling because the sky itself once carried an animal that still seems too large to belong there. Ask most people to imagine the largest flying animal, and the mind reaches for something familiar. A giant eagle, an enormous bat, maybe a bird with a wingspan stretched to an unrealistic extreme. Quetzalcoatlus northropi was none of those things. Quetzalcoatlus northropi was a pterosaur, a flying reptile from the late Cretaceous. Quetzalcoatlus northropi was not a dinosaur, even though Quetzalcoatlus northropi lived in a world where dinosaurs dominated the land. The anatomy of Quetzalcoatlus northropi followed a different set of rules from the anatomy of birds, and those rules allowed a scale that still feels difficult to accept. Wingspan estimates for Quetzalcoatlus northropi commonly fall around 10 to 11 meters, with some discussions reaching near 11 to 12 meters depending on the reconstruction. The exact numbers remain debated, but the central point is solid. Quetzalcoatlus northropi was one of the largest flying animals ever known. That creates an immediate contradiction. Flight demands lightness. Gigantism demands structure. Modern animals rarely combine those demands at such extremes. But pterosaurs were not flying with feathered wings like birds. The wing of Quetzalcoatlus northropi was a membrane supported largely by an enormously elongated fourth finger. The bones of Quetzalcoatlus northropi were lightweight. The anatomy of Quetzalcoatlus northropi was specialized. The entire body plan of Quetzalcoatlus northropi was built around a different aerodynamic solution. Quetzalcoatlus northropi was not a giant bird. Quetzalcoatlus northropi was a different answer to the problem of leaving the ground. The most famous fossils of Quetzalcoatlus northropi are associated with the Javelina Formation in the Big Bend region of Texas. The first key discovery was made in 1971 by Douglas Lawson, then a graduate student at the University of Texas at Austin. The species name northropi honors John Knudsen Northrop, an aviation pioneer, while the genus name refers to Quetzalcoatl, the feathered serpent deity of Mesoamerica. Even the name seems built for the air, but the environment was not a perfect fantasy of sea cliffs and steady ocean winds. The world of Quetzalcoatlus northropi was more likely a late Cretaceous floodplain system with meandering rivers, sediment channels, wooded zones near water, open ground, and a mix of animals living around the same landscape. Fossils from the broader region include fish, turtles, crocodiliforms, small mammals, dinosaurs, and pterosaurs. This matters because the old popular image of a giant pterosaur often kept the animal almost entirely in the sky, soaring like a living glider and landing only when necessary. Modern reconstructions have made that image less simple. Quetzalcoatlus northropi may have spent a great deal of time on the ground. And on the ground, Quetzalcoatlus northropi becomes even stranger, standing still. Quetzalcoatlus northropi was not just a pair of wings. Quetzalcoatlus northropi was a tall quadruped with a long neck, a long toothless beak, folded wings, and proportions unlike anything alive today. The forelimbs of Quetzalcoatlus northropi were part of the wing system, but on land, those same forelimbs helped support the body. Many reconstructions show Ajdarchid pterosaurs walking on all fours with an efficient and unusual gait. The result is not an eagle scaled up. The result is closer to a giant stalking stork, crossed with a glider and a reptile. That changes the fear. Quetzalcoatlus northropi was not only something overhead. Quetzalcoatlus northropi may have walked through floodplains, river margins, and open areas, searching for small animals, carrion, and other food opportunities. Some interpretations describe Quetzalcoatlus northropi as an opportunistic terrestrial forager, patrolling the ground with a long beak and enormous reach. A small animal in that landscape would not only fear teeth, claws, or an ambush from the water. A small animal might also face a silent shape moving across the plain on folded limbs, with the head of Quetzalcoatlus northropi dropping down like a spear. The takeoff problem makes Quetzalcoatlus northropi even more extreme. An animal with wings that large could not simply flap away like a small bird. Pterosaurs are often discussed in relation to quadrupedal launch, using powerful forelimbs as part of a vaulting motion to push the body upward. For a giant pterosaur, this strategy makes sense because the launch becomes a short burst of power rather than a long, vulnerable runway. Still, the exact mass and flight performance of Quetzalcoatlus northropi remain technical subjects of debate. Reconstructing a giant flying animal from incomplete fossils requires caution. A lighter model changes the possibilities. A heavier model changes them again. But the uncertainty does not make Quetzalcoatlus northropi less impressive. The uncertainty shows how close Quetzalcoatlus northropi lived to the edge of what powered flight can allow. That is the real tension. Quetzalcoatlus northropi was not strange because Quetzalcoatlus northropi violated physics. Quetzalcoatlus northropi was strange because pterosaur anatomy pushed physics into a region modern animals no longer occupy. The javelina landscape adds a lonely quality to the animal. Quetzalcoatlus northropi does not appear to have been especially common in those deposits. Some interpretations associate Quetzalcoatlus northropi with river channel settings rather than dense colonies. That fits the image of a large animal moving through riparian habitats, not necessarily filling the sky in flocks like seabirds. A giant that does not rely on numbers becomes dangerous in a different way. Presence replaces abundance. A late Cretaceous floodplain in Texas would not have felt empty. The air would be heavy. A river would cut through the landscape. Dinosaurs would move in the distance. Then a shape taller than a person could walk along the bank, wings folded, neck raised, long beak scanning the ground. The impossible part is not only that Quetzalcoatlus northropi could fly, The impossible part is that Quetzalcoatlus northropi could stand there, a living aircraft of bone, skin, muscle, and membrane, walking through a world that still had room for giants in the air. The fifth impossible animal brings the threat back down to land. When people hear the phrase predatory bird, the mind usually builds a hawk, an eagle, or a falcon. Wings control the attack. Talons strike from above. Death comes out of the sky. Kelenken guillermois was almost the reverse. Kelenken guillermois was a giant flightless bird from the Middle Miocene of Patagonia, Argentina. Kelenken guillermois belonged to Racidae, the terror birds, a family of large predatory birds that occupied major carnivorous roles in South America through much of the Cenozoic. That is hard for the modern mind, because large living birds rarely hold that kind of niche. Ostriches are mostly herbivorous or omnivorous runners. Condors are scavengers. Eagles and hawks are aerial hunters. A giant ground bird acting like a top-land predator feels misplaced. But in South America, for millions of years, terror birds were not misplaced. Terror birds were part of the system. The fossil history of Kelenken guillermois gives the animal an almost mythic quality. The name Kelenken refers to a giant bird spirit in Tehuelche mythology. The species name guillermois honors Guillermo Aguirre Zabala, the student who discovered the fossil near Comalo in Rio Negro province. The formal description came in 2007, based on an important specimen that included a remarkably complete skull, along with leg bones and a toe bone. The skull is the detail that changes everything. The skull of Kelenken guillermois was more than 716 millimeters long. More than 71 centimeters of head. For a bird, that is extraordinary. Kelenken guillermois is often discussed as having the largest known skull of any bird, or at least one of the largest ever recorded. And when a flightless predator carries a skull that large, the entire body begins to look organized around one brutal sequence. Run. Reach. Strike. The wings of terror birds were reduced and not functional for flight. The legs of Kelenken guillermois were built for movement on land. The neck of Kelenken guillermois worked like a powerful lever. The beak of Kelenken guillermois was not a delicate tool for seeds or fish. The beak of Kelenken guillermois was a weapon. But the way that weapon worked is more interesting than simple force. For years, terror birds were often imagined as skull-crushing machines. Biomechanical studies on Ambulocetus, a smaller terror bird, suggest a more precise picture. The skull of Ambulocetus handled vertical forces better than lateral forces. In practical terms, that points toward controlled downward strikes and pullback movements, rather than wrestling large, struggling prey side to side. Kelenken guillermois was not Ambulocetus, so the comparison must be used carefully. But the broader idea is useful. A giant terror bird may not have fought like a cat locking onto prey with teeth and claws. Kelenken guillermois may have attacked more like a living axe. The beak of Kelenken guillermois could drive downward. The neck of Kelenken guillermois could help deliver and withdraw the blow. The legs of Kelenken guillermois could keep the predator moving, allowing repositioning, repeated attacks, and pursuit across open terrain. That combination is frightening because the predator does not need to hold on for long. Holding on to large, struggling prey creates dangerous sideways forces. A strike and withdraw strategy avoids that problem. The predator hits, steps back, realigns, and hits again. For prey, the safest answer would be distance. But an open Miocene landscape does not always provide distance. The fossils of Kelenken guillermois come from deposits of the Collón Cura Formation, a formation associated with continental environments, including rivers, alluvial systems, and lakes. This was not the world of a cliffside hunter. This was a world of plains, banks, open spaces, and patchy habitats where long legs mattered. The time period also matters. Around the Middle Miocene, global climate experienced warm intervals that could support productive ecosystems and diverse prey communities. South America had its own native mammal faunas, with many animals unlike those on northern continents. Terror birds lived in a world where familiar, large, placental carnivores had not fully shaped every major predatory role. That left space for avian predators to matter. That does not mean Kelenkin Guillermois had to kill the largest animals in Patagonia. A predator does not need to specialize in giants to be terrifying. Kelenkin Guillermois could have targeted medium-sized prey, juveniles, weakened animals, or animals caught in bad terrain. The size of Kelenkin Guillermois, the legs of Kelenkin Guillermois, and the skull of Kelenkin Guillermois all suggest a predator capable of turning opportunity into violence quickly. The disturbing part is the mismatch with modern expectations. A bird should not be the thing running prey down. A bird should not have a skull built like a weapon mounted on a long neck. A bird should not replace the ecological feeling of a large mammalian carnivore. But Kelenkin Guillermois did, and Kelenkin Guillermois was not alone. Terror birds formed an entire family of predatory birds, with different sizes and adaptations, occupying roles across millions of years. Their existence proves that the Cenozoic world of South America had its own experiments in top predators, feathered, flightless, and armed with beaks instead of teeth. From a distance, Kelenkin Guillermois might not look supernatural. The silhouette of Kelenkin Guillermois would be tall, fast, strange, maybe almost elegant in a severe way. But the skull of Kelenkin Guillermois would change that impression immediately. That long beak was not built for song. That skull was not built for flight. That head was a weapon carried at running height across an open landscape. And if Kelenkin Guillermois saw prey first, the prey's problem was not the sky. The problem was the ground. The sixth impossible animal is not frightening because Chalicotherium goldfussi was a predator. Chalicotherium goldfussi was an herbivore. But Chalicotherium goldfussi looked as if evolution had taken a horse-like relative, rejected the expected design, and rebuilt the body from parts that seemed to belong somewhere else. Chalicotherium goldfussi was a perissodactyl, a member of the odd-toed ungulate lineage that also includes horses, rhinoceroses, and tapirs. That family connection creates expectations. The modern mind expects hooves. The modern mind expects column-like limbs. The modern mind expects running, grazing, or at least a body that moves across ground in a recognizable ungulate way. Chalicotherium goldfussi refuses that expectation. The forelimbs of Chalicotherium goldfussi were long. The posture of Chalicotherium goldfussi was unusual. Most importantly, the hands of Chalicotherium goldfussi ended in large claws. Not hooves, claws. That one feature breaks the mental category. A large herbivorous mammal related to horses and rhinoceroses should not have long arms and hooked claws. Yet the claws of Chalicotherium goldfussi were not mistakes. The claws of Chalicotherium goldfussi were tools. The type species, Chalicotherium goldfussi, was originally described from material found near Appenheim in Germany, in deposits known as the Dinotherian Sande. Over time, more evidence helped build a clearer image of the animal and the broader Chalicotheri family. These were not random, odd bones. These were members of a real and unusually successful lineage. The lifestyle of Chalicotherium goldfusi appears to have centered on browsing rather than grazing. That distinction matters. A grazer eats low vegetation, especially grasses in modern ecosystems. A browser feeds on leaves, shoots, twigs, and softer plant material from shrubs and trees. Chalicotherium goldfusi seems to have been adapted for reaching and manipulating vegetation rather than galloping across open plains. The long forelimbs of Chalicotherium goldfusi gave Chalicotherium goldfusi reach. The claws of Chalicotherium goldfusi may have helped hook branches and pull those branches toward the mouth of Chalicotherium goldfusi. Instead of evolving a giraffe-like neck, Chalicotherium goldfusi found another solution. Reach forward, pull food inward, feed with a body built for manipulation. That is why Chalicotherium goldfusi looks so strange. The design only becomes logical when the feeding problem is understood first. The claws of Chalicotherium goldfusi also shaped how Chalicotherium goldfusi moved. Many reconstructions suggest knuckle walking, with the forelimbs positioned in a way that protected the claws from being worn down against the ground. The image is almost surreal. A large, hoofed mammal relative moving in a way that evokes a gorilla. Not because Chalicotherium goldfusi was a primate, but because the body of Chalicotherium goldfusi needed to protect the feeding tools. Evolution arrived at a posture that looks borrowed from another lineage. The teeth of Chalicotherium goldfusi add another layer. Chalicotherium goldfusi appears to have relied on a browsing diet, with dentalware studies supporting the consumption of leaves, twigs, and possibly bark. The molars of Chalicotherium goldfusi were suited to processing plant material. Mature individuals may have lacked upper incisors and canines, relying more on lips and a gum pad to handle vegetation. In other words, the mouth of Chalicotherium goldfusi was not built for aggression. The hands of Chalicotherium goldfusi looked aggressive. The diet of Chalicotherium goldfusi was not. That contradiction is what makes Chalicotherium goldfusi so memorable. Chalicotherium goldfusi shows that claws do not automatically mean carnivory. A claw can be a hook. A claw can be a rake. A claw can be a branch-pulling device. A body part that looks like a weapon can evolve because food is hard to reach. Some skeletal interpretations suggest Chalicotheres could sit back on the hindquarters for extended feeding, using the body almost like a tripod. The pelvis and other skeletal features have been discussed in relation to this behavior. When visualized carefully, the scene becomes stranger than a predator attack. A large herbivorous mammal sits back. The hindquarters of Chalicotherium goldfusi brace the weight. The forelimbs of Chalicotherium goldfusi pull branches inward. The mouth of Chalicotherium goldfusi strips leaves and soft plant material. The animal feeds like a mixture of ground sloth, gorilla, horse relative, and bear-shaped browser. That is not random weirdness. That is functional convergence. Chalicotherium goldfusi has been compared in lifestyle or anatomy to ground sloths, great apes, bears, and even therizinosaur dinosaurs. Another famous example of large claws used in non-predatory contexts. When unrelated lineages arrive at similar solutions, the reason is usually pressure. Reach food, manipulate vegetation, defend the body when necessary. Do not depend completely on speed. And defense matters. Chalicotherium goldfusi was an herbivore, but herbivore does not mean the harmless. A large body with long forelimbs and claws would be risky to attack. A strike from the forelimb of Chalicotherium goldfusi would not need to kill a predator to matter. Injury can be enough. In nature, a wound can become a delayed death sentence through infection, starvation, or reduced hunting ability. For a predator, Attacking Chalicotherium goldfusi would require calculation. For Chalicotherium goldfusi, the same claws that helped feed the body could also discourage close contact. That makes Chalicotherium goldfusi an evolutionary contradiction only from the modern point of view. In the Miocene habitats of Europe, where wooded areas, shrubs, and varied vegetation created browsing opportunities, the body plan had logic. Chalicotherium goldfusi was not a badly assembled horse. Chalicotherium goldfusi was an herbivore that solved feeding through reach instead of speed. The seventh impossible animal seems less terrifying at first. Nigersaurus taketi was not a super predator. Nigersaurus taketi was not armed with giant claws or a crushing beak. Nigersaurus taketi was a sauropod, part of the broad dinosaur group famous for long necks, huge bodies, and plant-eating giants. That should make Nigersaurus taketi feel familiar, but the skull of Nigersaurus taketi breaks the familiar picture. Nigersaurus taketi lived during the early Cretaceous in what is now Niger in Africa. That region was not the Sahara Desert of the modern world. It was a landscape of rivers, floodplains, vegetation, and ecosystems capable of supporting large herbivorous dinosaurs. Nigersaurus taketi belonged to the Rhabachisaurid sauropods, a group within the larger sauropod world. But the feeding system of Nigersaurus taketi was nothing like the classic image of a high-browsing giant. The head of Nigersaurus taketi was extremely lightweight relative to the body. The skull bones of Nigersaurus taketi were thin and filled with openings. The muzzle of Nigersaurus taketi was broad and flat, and the teeth of Nigersaurus taketi were concentrated toward the front of the mouth in a highly specialized dental battery. This was not a simple head attached to a long-necked body. This was a feeding machine. Nigersaurus taketi is famous for having hundreds of teeth, including replacement teeth stacked inside the jaws. The exact count depends on how the teeth are counted, but the message is clear. The jaws of Nigersaurus taketi were built for constant wear and constant replacement. That tells us something important about daily life. Teeth do not become disposable unless the diet punishes them. Nigersaurus taketi appears to have fed at low levels, cropping vegetation close to the ground. Instead of lifting the neck high to strip branches from trees, Nigersaurus taketi likely kept the head low, using the wide mouth of Nigersaurus taketi to remove broad swaths of soft vegetation. Comparisons to a vacuum cleaner or lawnmower can help the viewer visualize the motion, but the real point is ecological, not comedic. Nigersaurus taketi occupied a low feeding niche. That niche matters because ecosystems with multiple large herbivores need ways to divide food. If one sauropod feeds high and another sauropod feeds low, direct competition can be reduced. Nigersaurus taketi may have specialized in plants that other giants did not prioritize, stripping vegetation from the lower layer of the habitat. The mouth of Nigersaurus taketi was not monstrous. The mouth of Nigersaurus taketi was efficient, and efficiency can be just as strange as violence. The orientation of the skull and jaws in Nigersaurus taketi has been discussed as evidence for low browsing. The wide muzzle, front-positioned teeth, and rapid tooth replacement all support an animal built to feed repeatedly and heavily near the ground. The action would have been constant. Bite, strip, replace, continue. In a clean modern garden, that might sound harmless. But the early Cretaceous ground layer was not clean. Feeding low means feeding close to sediment. Dust, grit, and abrasive particles become part of the meal. Even if Nigersaurus taketi was not intentionally eating dirt, the act of cropping vegetation near the ground would expose the teeth of Nigersaurus taketi to constant wear. The body's answer was not to preserve every tooth for years. The body's answer was to keep producing replacements. That is why Nigersaurus taketi feels almost industrial. Nigersaurus taketi was not strange, because Nigersaurus taketi was gigantic by sauropod standards. Many sauropods were larger. Nigersaurus taketi was strange because the skull of Nigersaurus taketi looked engineered for a narrow job. Wide muzzle, lightweight head, front teeth, replacement system, low feeding posture. Evolution had turned a sauropod into a ground-level harvesting machine. That changes how Nigersaurus taketi should be imagined. Nigersaurus taketi did not need to charge, roar, or dominate through aggression. The scene is colder, quieter, and more repetitive. A large herbivore moves slowly through an ancient floodplain. The head of Nigersaurus taketi stays low. The mouth of Nigersaurus taketi sweeps vegetation. The teeth of Nigersaurus taketi work through plant matter again and again. The ecosystem is reshaped not by a sudden attack, but by relentless consumption. That is another form of power. Predators create fear through sudden death. Large herbivores create ecological force through constant pressure. Nigersaurus taketi was not a monster in the usual sense. Nigersaurus taketi was a reminder that evolution can build specialized machines from living tissue, and some of those machines do not look dramatic until the function becomes clear. A sauropod does not have to reach the treetops to be extraordinary. Sometimes the strangest giant is the one built to keep the head down. The eighth impossible animal is small enough to seem harmless. That is part of the deception. Pagomastax africanus was not a giant. Pagomastax africanus was a small, early ornithischian dinosaur from southern Africa, usually imagined closer in size to a house cat or small dog than to a classic dinosaur predator. But the skull of Pagomastax africanus carries one of the most confusing faces in the dinosaur record. A beak at the front, a deep lower jaw, different types of teeth, and prominent fang-like canines. For an animal understood as primarily herbivorous, that combination feels wrong. Pagomastax africanus belonged to the heterodontosaurids, a group of small ornithischian dinosaurs known for having different kinds of teeth. The group name comes from that feature. Heterodont means different teeth. Unlike animals with one uniform tooth type, heterodontosaurids could combine beak-like structures, grinding or slicing teeth, and enlarged canine-like teeth. The fossil history of Pagomastax africanus is also unusual. Material was collected during a 1960s expedition in southern Africa, in what was then the Transkei region of South Africa. But the animal was not formally described until 2012 by paleontologist Paul Sereno. That delay is less strange than it seems. Museum collections can preserve fossils for decades before someone recognizes what those fossils truly represent. In the case of Pagomastax africanus, the most informative material included parts of the skull and jaws. And the jaws carried the mystery. The name Pagomastax means something close to strong jaw. That is not a throwaway detail. The lower jaw of Pagomastax africanus was deep and robust for such a small animal. The front of the mouth had a beak-like structure. The cheek teeth show adaptations for processing plant material. But the enlarged canine-like teeth create a visual signal that feels predatory. So why would a mostly plant-eating dinosaur have fangs? The answer is probably not simple carnivory. In heterodontosaurids, enlarged canine-like teeth may have served several possible functions. The canine-like teeth may have helped with defense. The canine-like teeth may have been used in display or threat behavior between individuals. The canine-like teeth may have played a role in sexual competition. The canine-like teeth may even have assisted with certain foods. The important point is that fangs do not automatically make Pegomastax africanus a meat eater. The wear patterns and jaw mechanics support an animal adapted mainly for processing plants. That makes Pegomastax africanus a biological contradiction only if modern categories are forced onto the animal. Herbivore and fang-bearer are not opposites. Many living animals use enlarged teeth for fighting, display, intimidation, or social signaling, while still eating mostly plants. The body covering of Pegomastax africanus is another place where caution matters. Some reconstructions show bristle-like filaments or quill-like structures on the body of Pegomastax africanus. That idea comes partly from related heterodontosaurids, such as Tian Yulong, where filamentous structures have been reported. But for Pegomastax africanus specifically, direct fossil evidence of preserved skin or filaments is limited. A bristly reconstruction is plausible within the broader group, but plausible is not the same as directly preserved. That uncertainty makes Pegomastax africanus more interesting, not less. Pegomastax africanus is not unsettling because every detail is known. Pegomastax africanus is unsettling because the known details are already enough to break the stereotype. A small dinosaur with a parrot-like beak and canine-like teeth does not fit the popular image of a dinosaur. Pegomastax africanus was not a tiny velociraptor. Pegomastax africanus was not a miniature triceratops. Pegomastax africanus was a compact, sharp-faced, plant-processing animal with a skull that looked ready for confrontation. In a Jurassic ecosystem, size does not have to be huge for survival to be complicated. Small animals live under constant pressure. Predators can strike from above, from vegetation, or from shadow. Food resources can shift. Competition with other small herbivores can be intense. In that context, a strong jaw and intimidating teeth may have mattered. Even a small animal benefits from making a predator hesitate or making a rival back away. Pegomastax africanus shows that evolution can make a tiny animal look more aggressive than the diet requires, and that appearance may itself have been part of survival. The ninth impossible animal became famous long before anyone understood the full body. For almost half a century, Deinocheirus mirificus was a dinosaur built mostly out of imagination. The first fossils, discovered in 1965 in the Gobi Desert of Mongolia, included enormous arms measuring about 2.4 meters long. The arms of Deinocheirus mirificus came with large hands and claws, shoulder elements, and scattered bones. But most of the skeleton was missing. That absence created a scientific ghost. The name Deinocheirus means terrible hand. For decades, that was the problem. 2 giant arms, almost no body. Theories formed around the missing animal. Some imagined Deinocheirus mirificus as a huge predator. Others suggested a strange, unknown lineage, or a bizarre, specialized dinosaur unlike anything else. The fossil record had given scientists enough evidence to make Deinocheirus mirificus unforgettable, but not enough evidence to make Deinocheirus mirificus understandable. Then the story changed. Additional specimens from the Namek Formation of Mongolia, excavated in 2006 and 2009, finally revealed much more of the animal. The story also involved fossil poaching. Some important bones, including the skull and parts of the hands and feet from one specimen, had been removed and sold before scientists could recover them. Later, some of the missing pieces resurfaced, allowing the puzzle to come together. What emerged was stranger than the old speculation. Deinocheirus mirificus was not a giant killer built around claws. Dinocyrus mirificus was an enormous ornithomimosaur, part of the broader group often called ostrich dinosaurs, but transformed into a form almost nobody expected. Most ornithomimosaurs are imagined as light, fast, long-legged animals. Dinocyrus mirificus was different. Dinocyrus mirificus was huge, heavy, and not built like a sprinter. Some reconstructions place Dinocyrus mirificus around 11 meters long and more than 6 metric tons. The exact numbers can vary, but the conclusion is secure. Dinocyrus mirificus was one of the largest known ornithomimosaurs, and the full body was almost absurd. The arms of Dinocyrus mirificus were enormous. The body of Dinocyrus mirificus was bulky. The hind limbs of Dinocyrus mirificus were relatively short for such a large animal. The back of Dinocyrus mirificus carried tall neural spines, producing a hump-like or sail-like profile. The skull of Dinocyrus mirificus had a long, broad snout, often compared to a duck-like beak. Taken together, Dinocyrus mirificus looked like a giant ostrich dinosaur crossed with a swamp forager, carrying monster arms, a broad beak, and a raised back. The diet made the picture even more surprising. The body cavity of Dinocyrus mirificus contained more than 1,000 gastroliths, stones swallowed to help process food. Fish remains were also associated with the gut contents. That points toward a broad omnivorous diet, including plant material and aquatic resources. Dinocyrus mirificus was not a classic carnivore, and Dinocyrus mirificus was not a simple herbivore. Dinocyrus mirificus appears to have been a huge opportunist, feeding on what the environment offered. The environment of the Nemegt Formation supports that interpretation. The Nemegt landscape is often reconstructed as a system of river channels, floodplains, and lake-like areas, wetter than some other Cretaceous environments in the region. This was a world of water margins, sediment, vegetation, and diverse dinosaur life. In that setting, Dinocyrus mirificus starts to make sense. The broad snout of Dinocyrus mirificus could help gather vegetation or food from shallow water. The large body of Dinocyrus mirificus provided protection through sheer mass. The claws of Dinocyrus mirificus may have been used for foraging, pulling vegetation, or defense rather than active predation. The gastroliths inside Dinocyrus mirificus helped process plant material. The fish remains show that aquatic food was also part of the story. This was not a monster designed to chase. This was a giant designed to exploit. That is why Dinocyrus mirificus is such a strong example of how incomplete fossils can mislead the imagination. When only the arms were known, the mind built the most dramatic animal possible. But the complete animal was not less strange. The complete animal was stranger because the truth did not match the obvious guess. The terrible hands did not belong to a super predator. The terrible hands belonged to a massive, swamp-edge omnivore. That reversal matters because paleontology changes not only what scientists know, but what kinds of animals people are able to imagine. Dinocyrus mirificus was not a fantasy creature. Dinocyrus mirificus was a working body plan in a specific ecosystem. The apparent absurdity becomes less absurd once the rivers, floodplains, fish, plants, and predators are restored around the skeleton. A huge animal does not need speed when size itself discourages attack. A huge animal does not need sharp teeth when a broad beak and digestive stones can process available food. A huge animal does not need to fit the category suggested by the first fossil. Dinocyrus mirificus was a reminder that sometimes the fossil record does not reveal a monster by showing the teeth. Sometimes the fossil record reveals a monster by showing the hands. and then waits nearly half a century to reveal that the hands belong to something even harder to categorize. The 10th impossible animal comes from a world before the famous dinosaurs existed. Before Tyrannosaurus, before Triceratops, before birds filled the sky, before flowering plants reshaped terrestrial ecosystems. In the Middle Permian, roughly 267 million years ago, Earth was already producing large, strange, heavy animals that looked like failed myths from a world not yet committed to reptiles or mammals. One of the most memorable was Ambulocetus mirabilis. Ambulocetus mirabilis was a therapsid, part of the synapsid line, more closely related to mammals than to modern reptiles. That relationship matters because the face of Ambulocetus mirabilis looks nothing like what most people expect from a mammal relative. The skull of Ambulocetus mirabilis was massive, sometimes described at around 65 centimeters long, and crowned with bony projections rising upward and outward from the head. These were not horns like the horns of a modern bull, with a bony core and a keratin sheath. These were bony outgrowths of the skull itself, forming a strange crown of knobs and branches. The name Ambulocetus is often translated as crowned crocodile. The name fits the first impression, but Ambulocetus mirabilis was not a crocodile. That is the first contradiction. The second contradiction is the diet. With a skull like that, a heavy body, and an alarming silhouette, Ambulocetus mirabilis can easily look like a predator. But Ambulocetus mirabilis is generally interpreted as an herbivore or possibly an omnivore, an early, large-bodied synapsid capable of feeding on vegetation and perhaps supplementing the diet with other resources. The ornamented head was likely not primarily a killing tool. The bony crown of Ambulocetus mirabilis may have been used for display, species recognition, intimidation, social signaling, or controlled contests between individuals. The crown of Ambulocetus mirabilis may have communicated maturity, strength, status, or identity. In other words, the most dramatic structure on the animal may have functioned as a message. That is stranger than a weapon. A weapon is easy to understand. A permanent crown of bone, used as social language, belongs to a more complicated animal. Fossils of Ambulocetus are known from the Perm region of Russia, including deposits associated with the Belebey Formation and local faunal zones. Multiple complete and incomplete skeletons have been reported, which means scientists are not working from one mysterious fragment alone. Ambulocetus was a real part of Middle Permian ecosystems. The body of Ambulocetus mirabilis was robust, with relatively short limbs and a posture that appears more sprawling or semi-sprawling than the posture of a modern mammal. That posture adds to the unease. Ambulocetus mirabilis looks like an animal caught between worlds. Not reptile, not mammal, not anything alive today. The body size was also significant. Ambulocetus mirabilis could exceed 3 meters in length. Even without being an apex predator, an animal of that size would command space. A heavy body, a broad skull, and a crown of bone do not need speed to matter. Presence itself becomes a defense. To understand Ambulocetus mirabilis, the environment has to come first. The Middle Permian world was moving toward the assembly and dominance of Pangaea. Landscapes included river systems, floodplains, sediment-rich basins, and vegetation made of ancient plant groups, including conifers and other non-flowering plants. No modern grasslands, no birds, no flowers, no familiar mammal communities. Instead, terrestrial ecosystems were filled with groups now extinct or almost unimaginable to the general viewer. Dinocephalians, dicynodonts, pterosaurs, biarmasuchians, and other synapsids and reptiles carrying the early experiments of land vertebrate evolution. Asteminosuchus mirabilis belonged to the dinocephalians, a group that became important in Middle Permian terrestrial ecosystems. These animals show that large land-bodied forms existed long before famous dinosaurs. The Permian was not an empty rehearsal before the real prehistoric world began. The Permian was already a world of giants, experiments, and ecological pressure. But that world did not last. Evidence points to a significant extinction event during the late Middle Permian, often associated with the Capitanian event, affecting marine and terrestrial ecosystems. The causes are discussed in relation to large-scale environmental disruption, including volcanic activity and climate change. Groups such as dinocephalians declined or disappeared in connection with these broader transformations. That gives Asteminosuchus mirabilis a darker meaning. Asteminosuchus mirabilis did not just have a strange skull. Asteminosuchus mirabilis represented a world that vanished. The mammal line continued in different forms, but the crowned, heavy, Baroque dinocephalian body plan did not become a familiar modern inheritance. Asteminosuchus mirabilis became a fossil signal from an ecosystem that tested one version of land vertebrate dominance, and then erased most of that version, except for bone. That is why Asteminosuchus mirabilis belongs with animals that feel like they should not have existed. Not because Asteminosuchus mirabilis was physically impossible, because Asteminosuchus mirabilis reminds us that evolution does not only produce efficient, clean, modern-looking designs. Evolution also produces theatrical bodies, exaggerated skulls, social weapons, and animals whose logic only becomes clear after the lost world around the skeleton is rebuilt. The crown of Asteminosuchus mirabilis may look like armor. The crown of Asteminosuchus mirabilis may have functioned as identity. The crown of Asteminosuchus mirabilis may look like threat. The crown of Asteminosuchus mirabilis may have been communication. And in a Permian floodplain under a sky with no birds, a heavy synapsid carrying that crown would have looked less like an ancestor and more like a warning from a world that almost became familiar, then disappeared. These 10 animals are not connected by one simple family tree. Ambulocetus natans was part of the whale transition. Titanoboa cerrejonensis was a giant snake from a hot, post-dinosaur rainforest. Jacolopterus rhenanii was an armored arthropod predator from a time before vertebrates fully owned aquatic power. Quetzalcoatlus northropi was a flying reptile that pushed the limits of scale. Kelenken guillermois was a flightless bird that turned the ground into hunting territory. Chalaecotherium goldfusi was a clawed herbivore that rewrote what a hoofed mammal relative could look like. Nigersaurus taketi was a sauropod transformed into a low-feeding dental machine. Pegomastax africanus was a small plant eater with a face that refused to look harmless. Dinochirus mirificus was a giant ornithomimosaur that turned terrible hands into a half-century mystery. Asteminosuchus mirabilis was a crowned synapsid from a vanished Permian experiment. What connects these animals is not appearance. What connects these animals is pressure. Each animal existed because a particular world made a particular body useful. The estuary rewarded a walking whale that hunted the border zone. The Paleocene heat rewarded a snake larger than modern instinct wants to allow. Devonian waterways left room for armored arthropods to become terrifyingly large. Late Cretaceous skies and floodplains allowed a pterosaur to combine walking and flying at a scale that still feels unreal. South American ecosystems gave birds the chance to become ground predators. Miocene woodlands allowed a hoofed mammal relative to trade hooves for claws. Cretaceous river systems let a sauropod specialize in low vegetation with a mouth full of replacement teeth. The prehistoric world was not stranger because nature was less organized. The prehistoric world was stranger because the rules were different. And when the rules change, bodies change with them. That is the real lesson behind these animals. The fossil record does not simply preserve monsters. The fossil record preserves solutions, some elegant, some brutal, some awkward, some almost impossible to accept from a modern point of view. A skeleton can look ridiculous until the environment is rebuilt around the skeleton. Then the joke disappears. The walking whale becomes an ambush predator. The giant snake becomes a climate signal. The sea scorpion becomes an apex hunter before sharks ruled the story. The giant pterosaur becomes a terrestrial stalker with wings. The terror bird becomes South America's answer to the large carnivore. The clawed herbivore becomes a browsing machine. The strange sauropod becomes an ecosystem-level feeding tool. The fanged small dinosaur becomes a reminder that teeth can signal more than diet. The terrible hands become part of a giant omnivore shaped by rivers. The crowned synapsid becomes proof that social display was already being carved into bone long before modern mammals existed. None of these animals should feel normal. That is the point. Normal is only what survived long enough for humans to get used to seeing it. Deep time was full of other answers. Most of those answers are gone. What remains are bones, impressions, measurements, broken skulls, isolated vertebrae, enormous arms, and the occasional fossil that forces the modern mind to accept something uncomfortable. Evolution was never trying to make the world familiar. Evolution was only trying to make survival look reasonable. And sometimes, the only reason an animal looks impossible is because the world that made that animal possible is gone.